Often we will not have a functional relationship between x and y that describes the shape that we're trying to find the area and the centroid of. And in these instances, we might be able to break our shape into more easy to calculate shapes. So with the integral method, we basically broke our shape up into an infinite number of rectangles, added all of their areas together to find the total area, found the weighted average of their centroids to find the centroid of the total shape. Whereas here, we're going to break our shape into a finite number, usually only a few subshapes, and then individually for those subshapes, we're actually going to do the same process as we did in the integration, but we're going to do it manually per shape. We're going to find each shape's area, and we're going to find the centroidal location of each shape relative to the origin. So for this course, we're going to break it up into subshapes whose area and centroid is easy to find. And those examples we'll see on the following slides. Things like rectangles, right triangles, quarter circles, half circles, full circles. And what we can do is build our shape up with these positive shapes of rectangles, triangles, etc. Or we can build our shape up and then also make cutout shapes that we're going to represent using negative areas. But we're going to partition our shape into these easily identifiable and calculatable subshapes. So what we're going to do is we're going to make a table like this for our shape. So we're going to identify, and I do it by number here, the subshapes. Here, for example, 1, 2, as many as we have, of the subshapes that make up our total shape. And for each one of those, we are going to calculate its area, which is usually pretty easy to calculate. And then the x centroidal location, that's x tilde, y tilde here for each of those shapes with respect to a common origin. We're going to multiply that subshape's area by its centroidal locations x and y. Then when we do that for each of the shapes, we're going to sum down the columns. We're going to sum the total area of our shape and then the total of ax tilde and ay tilde. We don't need to sum our x tilde, y tilde. That's not going to provide us any information. So by summing down the columns, we find the summation of all the ax tildes for every subshape and ay tildes for every subshape. Then we're going to be able to find x bar and y bar using the same idea that we used for the calculus method, for the integral method, that if we take the total ax tilde divided by the total a, well, that's going to tell us x bar. If we find the total ay tilde divided by the total area, that is going to give us y bar. So because we have a few and a finite number of these subshapes, we can manually do what the integral was kind of automatically doing for us before, but that was for an infinite number of shapes, and now we're going to have just a couple of shapes. And we're going to see that this tabular method, where we're breaking it up into these shapes, can also be extended to work for 3D shapes and work for not only centroids, but also to find the center of mass. When we have objects that have different densities, we're going to be able to modify this slightly and make those calculations as well. So what are these smaller subshapes whose areas and centroids are going to be easy to calculate? Well, here's a sampling of ones we might see in this course. So here, a quarter circle. We can see how we can calculate where its centroid is relative to the flat edges of it. And we can find out what its area is. So the area is a quarter that of a full circle, and the centroid from the flat edges is going to be located 4r over 3 pi away. We might see semicircles, very similar idea. The area is half that of a full circle, and its centroid is 4r over 3 pi, 4 times the radius over 3 pi from the flat edge. Full circle, its centroid is going to be at the center of the circle, and we know the full area is pi r squared. For a rectangular area, its centroid is going to be at half of its height and half of its base, and its area is just base times height. And triangular areas, usually we're going to see this in the form of a right triangle, but the area is 1/2 the base times the height, and the centroid is going to be located 1/3 of its height and 1/3 of its base away from the right angle. And this chart has other shapes that we probably will not see in this course, but it's a good reference if we want to know where the centroidal location is. And as a future note, there's these calculations, these Ix, Iy. These are going to be the area moments of inertia that we're going to be using in later sections.